Welcome to this lecture on single-electron tunneling and Coulomb blockade in nano devices. Today we will explore one of the most fascinating quantum phenomena in nanoscale electronics. Let me start with a paradox. Imagine you have a tiny conducting island, just a few nanometers in size. You apply a voltage to make current flow through it. But nothing happens. The current is completely blocked. Then you add just one electron to this island, and suddenly current starts flowing. Why does adding a single electron change everything? This seems paradoxical from classical physics, where conductors behave smoothly. But at the nanoscale, charge quantization dominates. The foundation of this phenomenon is charge quantization. Electric charge comes in discrete packets, each carrying the elementary charge E, which is approximately 1.6 times 10 to the minus 19 coulombs. This is the elementary charge, the smallest unit of charge that exists freely in nature. In ordinary macroscopic conductors like wires, billions of electrons flow every second. The discreteness of charge is completely invisible. Current appears continuous. But when you shrink your device to nanometer scales, suddenly individual electrons become significant. You can count them one by one. Let me describe the typical experimental setup. We have a small conducting island, called a quantum dot or metallic island, connected to two electrodes through tunnel barriers. Here is the structure. The quantum dot sits between source and drain electrodes. The dashed lines represent tunnel barriers, thin insulating layers that electrons can quantum mechanically tunnel through. What exactly are tunnel barriers? They are thin insulating layers, typically made of oxide or vacuum gaps, just a few nanometers thick. Classically, electrons should not be able to cross an insulator. But quantum mechanically, there is a probability that an electron can tunnel through the barrier. This is pure quantum mechanics. The quantum dot has a very important property, its capacitance. Because the island is so small, its capacitance is extremely tiny. Capacitance relates charge Q to voltage V. For a sphere of radius r, capacitance is proportional to r. For a small metallic sphere, capacitance is approximately 4 pi epsilon 0 times the radius. If the radius is just 10 nanometers, the capacitance is incredibly small, around 1 attofarad. Now comes the crucial concept, charging energy. The energy required to add one electron to the quantum dot is given by the electrostatic energy. The charging energy E sub c equals E squared divided by 2c. This is the electrostatic energy cost of adding one electron to a capacitor. For nanoscale capacitors, this charging energy becomes enormous compared to thermal energy. Let me show you why this matters. If capacitance is 1 attofarad, which is 10 to the minus 18 farads, then the charging energy is approximately 12.8 millielectron volts. Compare this to thermal energy at room temperature, which is about 25 millielectron volts. They are comparable. At low temperatures, say 1 Kelvin, thermal energy drops to about 0.1 millielectron volts. Now the charging energy completely dominates. This is when Coulomb blockade appears. Now we arrive at the heart of the phenomenon, Coulomb blockade. Let me explain what happens when you try to push an electron onto the quantum dot. Here's a question. If there's a tunnel barrier, why can't the electron just tunnel onto the quantum dot? After all, quantum tunneling should allow this. The answer is energy conservation. To add an electron, you must supply the charging energy E sub c. If the applied voltage doesn't provide enough energy, tunneling is energetically forbidden. Imagine the quantum dot already has n electrons. An electron approaches from the left. It wants to tunnel on. But there's a huge electrostatic energy barrier, the charging energy. Without sufficient applied voltage, the tunneling is blocked. This is Coulomb blockade. The electrostatic repulsion from the electrons already on the island prevents additional electrons from tunneling on. Current is completely suppressed. How do we break this blockade and restore current flow? We need to provide enough energy to overcome the charging energy. The condition is that E times the applied voltage V must be at least equal to the charging energy E sub c. This gives us a threshold voltage. V must be greater than or equal to E divided by 2c. Below this voltage, no current flows. Above it, current suddenly appears. Here is the current voltage characteristic. At low voltage, current is 0 due to Coulomb blockade. At the threshold voltage, current suddenly jumps and starts flowing. This sharp transition is the signature of single-electron effects. Now let's add another layer of complexity: discrete energy levels. When the quantum dot is small enough, quantum confinement creates discrete energy levels, just like in an atom. When you confine electrons to a region smaller than their de Broglie wavelength, energy levels become quantized. The quantum dot behaves like an artificial atom. For a particle in a box of length L, energy levels are proportional to n squared h squared divided by 8 meters L squared, where n is the quantum number. Here are the discrete energy levels in a quantum dot. Electrons can only occupy these specific energy states. This quantization adds another condition for current flow. For an electron to tunnel onto the quantum dot, not only must the charging energy be overcome, but the electron must also find an available energy level to occupy. The Fermi energy in the lead must align with an available energy level E sub n, plus the charging energy E sub c. This is called resonant tunneling. When you vary the gate voltage applied to the quantum dot, you can tune the energy levels up and down. This creates periodic oscillations in the conductance. As you sweep the gate voltage, the conductance shows periodic peaks. Each peak corresponds to an energy level, aligning with the Fermi energy in the leads. Each conductance peak corresponds to adding one electron to the quantum dot. Between peaks, the system is in Coulomb blockade. This periodic behavior is called Coulomb oscillations. Let me give you a concrete example: the single-electron transistor, or SET. This is a practical device based on Coulomb blockade. The single-electron transistor has a source, drain, and gate electrode. The gate voltage controls how many electrons sit on the island, thereby controlling the current from source to drain. By adjusting the gate voltage, you can control the number of electrons on the island with single-electron precision. This allows switching current on and off by adding or removing just one electron. Let me give you an analogy to make this more intuitive. Think of the quantum dot as a revolving door or turnstile that only allows one person through at a time. People can only enter the turnstile one at a time. Once someone is inside, the next person must wait until the first person exits. Similarly, electrons must enter and leave the quantum dot one by one. When the charging energy is large and temperature is low, the quantum dot effectively allows only one electron to tunnel on at a time. This creates a precisely controlled current of individual electrons. Here's an important question: why don't we see Coulomb blockade in ordinary wires? Why is this special to nano devices? The answer is capacitance. In a macroscopic conductor, the capacitance is enormous, maybe picofarads or nanofarads. This makes the charging energy E sub c negligibly small, much smaller than thermal energy. For large capacitance, charging energy is much less than thermal energy K sub Bt. The discrete nature of charge is completely washed out by thermal fluctuations. But in nano devices at low temperatures, the charging energy dominates. Now the discreteness of charge becomes visible and controllable. Temperature plays a crucial role in observing Coulomb blockade. Let me explain why low temperatures are essential. For Coulomb blockade to be observable, thermal energy K sub Bt must be smaller than the charging energy E sub c. At room temperature, thermal fluctuations are large enough to overcome the charging energy barrier. Electrons can gain enough energy from thermal fluctuations to tunnel onto the island. At liquid helium temperatures, around 4 Kelvin, thermal energy drops dramatically. Now the charging energy barrier becomes insurmountable without applied voltage, and Coulomb blockade emerges clearly. Let's discuss the applications and implications of single-electron tunneling and Coulomb blockade. These phenomena are not just academic curiosities. Single-electron transistors could enable ultra-low power electronics. Since they control current one electron at a time, the power dissipation can be extremely small. In quantum computing, quantum dots can serve as charge qubits. The presence or absence of a single electron represents the quantum bit states 0 and 1. In metrology, single-electron tunneling enables precise current standards. By clocking electrons one by one through a device, you can generate a current that is exactly n times E times frequency. Single-electron pumps can transfer charge with extraordinary precision, 1 electron per cycle. This has applications in quantum metrology and nanoelectronics. Let's return to our initial paradox. Why does adding one electron suddenly change everything? In ordinary macroscopic conductors, the huge number of charge carriers and large capacitance make charge appear continuous. You never notice individual electrons. But in nano devices, the tiny capacitance means each electron costs a significant amount of electrostatic energy. Adding one electron changes the electrostatic potential of the entire island. This energy cost is what creates the discrete, quantized behavior. Current can only flow when the applied voltage provides enough energy to pay the charging cost for each electron. What are the key experimental signatures that tell you you're seeing Coulomb blockade? First, conductance is suppressed at low bias voltages. There's a gap in the current voltage characteristics centered at zero bias. Second, conductance shows periodic oscillations as you sweep the gate voltage. These are the Coulomb oscillations we discussed earlier. Third, the effect strongly depends on temperature. As temperature increases, the blockade features smear out and eventually disappear. Fourth, if you plot the charge on the quantum dot versus gate voltage, you see a staircase structure. Each step represents adding exactly one electron. Let me mention one advanced phenomenon: co-tunneling. Even in the Coulomb blockade regime, there can be a small residual current. Co-tunneling is a higher-order quantum process, where an electron tunnels onto the island, and simultaneously another electron tunnels off. This happens virtually, without the island ever having the extra charging energy. Co-tunneling allows a weak current to flow, even when direct tunneling is blocked. The current is much smaller than the direct tunneling current, but it's not zero. Let's compare quantum dots to classical capacitors to highlight what's different. In a classical capacitor, capacitance is large, charge appears continuous, and charging energy is negligible. In a quantum dot, capacitance is tiny, charge is quantized, and charging energy dominates. This fundamental difference creates completely different physics. Let me summarize the key concepts we've covered in this lecture. First, charge quantization becomes experimentally visible and important when you shrink devices to nanometer scales. Second, the charging energy E sub c creates electrostatic barriers that prevent electrons from tunneling onto the quantum dot. Third, Coulomb blockade is the suppression of current at low applied voltages due to the charging energy barrier. Fourth, discrete energy levels from quantum confinement add additional resonance conditions for tunneling. Fifth, whether you observe Coulomb blockade depends on the ratio of charging energy to thermal energy. Low temperature and small capacitance are essential. Sixth, in these devices, adding or removing a single electron can turn current completely on or off. Single electrons control macroscopic behavior. Let me conclude with some open questions and future research directions in this field. One major challenge is achieving room temperature operation. Current devices require cryogenic cooling. Can we engineer systems with such small capacitance that charging energy exceeds room temperature thermal energy? How do we integrate single-electron transistors with conventional CMOS technology? This is crucial for practical applications. What happens when multiple electrons occupy the quantum dot? Electron-electron interactions create complex many-body physics that we're still exploring. Can Coulomb blockade phenomena be harnessed for quantum information processing? Charge qubits and spin qubits in quantum dots are active research areas. Single electron tunneling and Coulomb blockade reveal the profound consequences of charge quantization at the nanoscale. What seems paradoxical from a classical viewpoint, that one electron changes everything, becomes natural when we account for the discrete nature of charge and the huge electrostatic energy costs in tiny capacitors. This field beautifully bridges fundamental quantum mechanics with practical nanoelectronics. It shows how quantum effects that are usually hidden become dominant and controllable. Understanding and controlling single electrons opens new technological possibilities, from ultra-sensitive electrometers to quantum computing platforms to fundamental tests of quantum mechanics. Thank you for your attention. I hope this lecture has given you a solid understanding of single electron tunneling and Coulomb blockade, and sparked your curiosity about the fascinating quantum world at the nanoscale.